Pipeline inspection. I'll straight away go into the subject without wasting much of time, because other things we all are professionals, most of it we know. The pipeline can be treated as a large pressure vessel. It is exactly a large pressure vessel. The problem with the pipeline inspection is that conventional NDT is not feasible in this case, simply because pipeline is not accessible. The other methodology that is normally adopted for testing the pipeline is hydrotesting, but hydrotesting itself has got a lot of limitations. The biggest limitation is that this is a fail or no fail test. The limiting defects which may survive the hydrotest, and then again the pipeline is put into operation, the pipeline can fail in a very short span of time. The other problem is interruption of supplies. If we are going to hydrotest the pipeline for inspection purposes, obviously we have to shut down the pipeline. So there will be interruption in supplies, availability of large amount of clean water. Then after hydrotesting, disposal of this contaminated water, safety of public at large during hydrotesting. And last but not the least, hydrotesting does not tell us what is the health of the pipeline. It's a simply fail, no fail, that's all. That's the biggest limitation. However, even with these limitations, hydrotesting continues to be practiced for new pipelines or for large-scale rehabilitation projects. Now, in the first half of the day, there was a lot of talk about non-piggable pipelines. Let's spend a couple of minutes on the non-piggable pipelines. First of all, let's understand what makes the pipeline non-piggable. It's not only non-availability of launcher and receivers. That's not a big constraint. The other problems are bigger constraints. One is no provision for launcher receiver. That is anyway a constraint. Reduced bore mainline walls and check walls. If reduced bore walls are there, the pig is going to get stuck and you cannot do any type of pigging on those lines. Next one is low flow conditions resulting in reduced velocity. If the pipeline diameter is large, the flow is less through that, therefore the velocity of the fluid will be very low. And in very low velocities, pigging, particularly instrumental pigging, is not possible. Then if we have bends which are less than 3D bends, there is every possibility of pig getting stuck at those locations. And lastly, if we have large diameter unbarred T, the pig is likely to get stuck in those locations. So non-piggability is attributed to many causes, and any one of them existing in the pipeline, they will make it non-piggable. Now what to do? What is the inspection technique for non-piggable pipelines? As in the morning it was discussed at length, ECDA and ICDA, that is external corrosion detection and internal corrosion detection, for which we have NACE standards RP 0502 and SP 0208. They actually, in a structured manner, they enumerate several activities which are to be carried out for non-piggable pipelines. And then this will give us a reasonably good estimate of the pipeline health. For example, they will say CPL survey, DCVG survey and other corrosion control surveys. For internal corrosion, corrosion probes are to be put. There is one more technique which has come recently, that is guided wave inspection technique. And OISD has issued a standard GDN 233 guidelines on inspection of on-land non-piggable pipelines. Now other things are well known, CPL, DCVG, corrosion probes. Let's see what is this guided wave inspection technique. This is the picture which shows basic principle of guided waves. Longitudinal guided waves are induced into the pipe body. When these waves intersect any pipe anomaly, mode conversion takes place into the laminar waves and reflect back to the tool original location. These reflected signals are digitally captured and processed. The whole process is known as teletest, and teletest equipment, hardware and softwares have been developed by the Welding Institute UK on this principle. Let's see what is involved in teletest. The teletest equipment system, the basic teletest system based on long range ultrasonic testing, that is LRUT, what I was talking in the morning. This comprises of the following. One is low frequency flaw detector, the teletest focus pulsar receiver unit, transducer ring or tool that wraps around the pipe, a laptop computer that contains the software controlling the system, cable connector between the teletest focus unit and tool, and communication between the teletest focus unit and laptop through Ethernet. This is how a teletest equipment looks like. This is the hardware which is involved in this. Incidentally, it is not only the Welding Institute UK who is doing this, who is performing this job. They have established an office in Madras, and this facility, if anybody wants, it can be accessed from their Madras office, and the concerned people are available who can come and do this. The only problem with this, or the only limitation, main limitation of this system is that in one setting, it can inspect about 3.5 kilometers, 1.5 kilometer on either side. So only small length pipelines can be inspected, and then every 3 kilometers we have to dug out, expose the pipeline, coating need not be removed, and then this ring has to be mounted. So every time 3 kilometers roughly you will get the data.
No sir, it is as per for buried pipeline, you have lot of limitation. It will give you only the light wave can travel up to somewhere it is less than 20 meters only.
No, the latest equipment which TWI has developed, they have confirmed that it will go on either side 1.5 to 2 kilometers.
It depends the depth of the pipeline as well as, and only few days back I come across this instrument and we got it done through TechCore. They have the same instrument by teletest, and somewhere it gives results up to 7 meter also.
Up to 7
meters in either side means 14 meter.
Only.
So it has very limited, it is very, I can say less effective in case of a buried pipeline, but yes, above ground pipeline it's very effective, and it may give you around 300-400 meters also. The record is 600 meters world level, at international level.
Have you used this?
Few days back I have used this.
Pardon?
Few days back I have used this.
Few days back, very
Yes, yes.
nice. You have taken the equipment from TWI?
No, it is TechCore. TechCore is a USA based company. They have their office in Mumbai, so we have hired their services and they came here in Delhi.
I would request you one thing, please have a dialogue with TWI UK.
Yes, sir.
Because their claims will not go just like that.
Yes, yes.
Because they are claiming 1.5 kilometer on either side. That is what they have claimed, without any limitations.
No, maybe for above ground pipeline, insulated
It's
lines.
not above ground, they say underground.
Buried it's not possible. It's not possible.
I don't know. I cannot say because
Yes, yes.
it is their claim. They say their development, their proprietary. They claim that 1.5 kilometers.
Actually, it depends
In
upon
fact, they say 1.5 to 2 kilometers.
It depends upon the frequency also. Actually, they choose the correct frequency.
That's
for
what
the
I'm
guided
saying.
waves.
That's what I'm saying. If you go to the person or you go to the agency.
No, in their software, there is in the drop down menu, there are so many frequencies. You have to choose the correct frequency to guide the waves.
Yes, that is correct.
I think there will be sensitivity
Yes,
difference between the two equipments.
Maybe.
But basic principle is
Principle is okay. It's wonderful tool for the above ground pipeline, particularly the insulated pipeline. But for the buried pipeline, underground pipeline, it has a very limitation, lot of limitations.
आप एक बार TWI UK से बात करो.
करते हैं सब.
हाँ, उनसे बात करिए, and I am sure they will come out with what is the limitation because they cannot put claims otherwise.
Okay, sir.
Now, what is the objective of inline inspection? The ultimate idea is that we go for inline inspection. Now, what is the objective? Objective is to determine the health of the pipeline in quantifiable terms so that we can measure the health of the pipeline in a mathematical manner. Okay, that means quantifiable terms is very important. To determine if any defect detected by online inspection would fail, not fall, it would fail at the operated pressure. To determine if any existing defect can extend and cause failure at the operated pressure. To consider all other factors, that is cracks, extensive fracture propagation, which could conceivably influence the integrity of the pipeline at the operated pressure. These are the objectives of inline inspection. Now, keeping these objectives in mind, the tools have been developed by different agencies, and today inline inspection or corrosion detection inspection is an activity which is performed by several companies across the globe. Now, classification of pipeline anomalies, let's go through this. I think as a pipeline professional, we all know very well that all the anomalies on the pipeline are not injurious and they need not be removed. So there are three classifications have been accepted by the industry. One is called imperfection. There is just an imperfection, but it is not going to cause any failure in the pipeline. The next one is defects. It will fail at or below the pressure that causes nominal yield of the pipe. And third one is the critical defect. This will fail at or below the maximum allowable operating pressure. This is the most critical defect. What are the different types of anomalies on a pipeline? One is metal loss, corrosion and gouges. The other are metallurgical defects like hard spots, inclusions, laminations and weld porosity. Cracks, which could be axial or circumferential. Dents and buckles with or without metal loss. This is how, it is a graphical representation of methods of defining severity of a metal loss anomaly. What is shown here is for different lengths of the pipeline, and these are for a 36-inch dia pipeline. 0.375 inches is the thickness, wall thickness. It's simply a graphical representation. Now, there will be 2-3 issues which are the main topic I will be talking. One is design and construction of the intelligent pig tools with a specific emphasis on magnetic flux leakage tools. That is the design and construction of MFL tools. And second one is design of the pipeline where a MFL tool can pass easily. What is needed out of that? And then execution of intelligent pigging. First, let's talk about the designing a pipeline for pigging, that is basically intelligent pigging. Now, as we all know, ideal pipeline would be a perfect straight line from end to end, have a constant ID with no weld penetrations, be perfectly round, have an inside surface which was polished or epoxy coated, have no offtakes, contain no valves or any other device, be pumping a light refined oil at a speed of about 1 meter per second, should be equipped with suitably designed pig launchers and receivers. Now, this is a utopia we are talking. This does not exist in practice. All the lines will be having bends. They will not necessarily, they will have constant ID. They will not be perfectly round. And all these things will not be actually existing on the pipeline. But still, the tools have been designed which can overcome all these problems. Now, what is intelligent pigging? This can be defined as the pigging that generates and records some data for analysis for establishing the health of the pipeline segments in quantifiable terms. If you look at the entire scenario of the pigging, there are basically two types of piggings. One is utility pigging, other is intelligent pigging. Now, utility pigging basically does not generate any data. For example, pipeline cleaning, during hydro testing, during drying, during internal coating, condensate removal, product separation, batching pigs, decommissioning the pipeline. This will not generate any data. This will only do the job for you. Intelligent pigs are fundamentally two types. One is geometry pigs, other is corrosion monitoring pigs. Now, corrosion monitoring pigs, one is based on MFL principle, other is based on ultrasonic principle. And now these conventional MFL tools, based on MFL principle tools, they are three types: conventional pig tools, high resolution pig tools, transverse field inspection pig tools. Geometry pigging, the objective is to find out the location and size of dents and ovalities in the cylindrical geometry profile of the pipelines. Now, what is the need of this? Let's question this. The basic need is the area of dent can be a stress riser, and already the pipeline is under stress due to internal pressure, due to bending of the plate, and maybe some additional stresses, welding stresses, all those. And if further additional stresses are introduced because of the dents, and if these dents incidentally fall on the either a girth weld or a longitudinal weld, then it becomes all the more serious. That's why it is essential to find out the geometry, absolutely. This is a typical electronic geometry pig tool. Its principle is very simple. As we can see, we have got sensing fingers. Then there is a pushing flange given here in the center. There is a transmission disc. I will tell the function of each component. Then we have a drive cup. Then we have a locator unit attached to this. There are odometer wheels on this, and there is a digital data recorder. Now, as the pig travels in this pipeline, geometry pig travels, if there is a dent, then these fingers will get depressed. And this depression will be communicated via the pushing flange to a potentiometer which is installed here inside. And the function of this potentiometer is to convert this mechanical signal into electrical signal. And this electrical signal will go to the recorder this will go to the recorder where it is recorded in digital form. Odometer wheel will measure the distance travelled by the tool. Locator unit, it is attached here with the pig tool. Its function is to find out the location of the pig when it is moving inside the pipeline. Drive cup is the front cup. That is the way the picture has been shown. From left side to right side it will be moving under pressure of gas or liquid or compressed air, whatever it is. Now we will talk about the MFL tool, construction of an MFL tool. And before we embark upon the construction, we must know what is the principle of magnetic flux leakage. Because geometry tool was very simple, it was based on the mechanical compression and then converting the data. This is little complicated. If we see here, this is the pipeline shown here, having a defect on the external surface and a defect on the internal surface. there is a magnet, permanent magnet, and there are sensors. Several sensors are there. They are fitted circumferentially. Okay. Now, these red color lines which are shown here, they are a representation of the magnetic flux. Okay. Now, wherever the strength of these magnets is manipulated in such a way so that the pipeline thickness gets literally, for all practical purposes, saturated with magnetism. Okay, if we subsequent slides will show what do I mean by saturated. So that it gets saturated with magnetism, and once it gets saturated, wherever the thickness is low, that is wherever there is a corrosion, external or internal, the entire flux is not able to get accommodated into the reduced thickness. Therefore, it will leak out. And that is known as flux leakage. And that is why the name magnetic flux leakage. Okay. Now, this magnetic flux leakage is captured in the sensors which are shown here, X, Y, Z. What is shown here? Why this X, Y, Z? You see, magnetic lines of force, they are representing the force, and force is a vector quantity. This can be analyzed into three components: X component, Y component, and Z component. So this is the representation of the sensor. Then we have a odometer wheel exactly for measuring the distance. So basic principle is that the line should be saturated, and as the tool moves, wherever there is a defect, there will be a flux leakage. That is, the magnetic flux lines of force shall leak out. Okay, whether the defect is internal or external, in either case. Basic principle of ultrasonic tool is very simple. It is exactly the same principle as we measure in case of a, let's say, pressure vessel or any other measuring. There is a transducer, external defect, internal defect, remaining wall thickness T will be equal to L1 minus L2. The transducer will be sending the ultrasonic waves. They will be, part of them will be absorbed, some of them will be returned back. The time difference between the two will be measured, and thickness loss, thickness remaining will be L1 minus L2 as shown here. So capital T minus small t, that will be the thickness loss, that is the defect. Now coming to intelligent pick tool selection, this is by far the most important thing for a practical engineer, because as I said, there are many type of intelligent pick tools available. If we look at the table shown here, magnetic flux leakage is, one is standard resolution MFL, high resolution MFL tool, ultrasonic compressed wave tool, then crack detection tool, ultrasonic and transverse MFL. And of course, caliper tool. Caliper is for geometry. So how to select the tool? This is exactly, I will just not go every word by word in this. That will be a lot of wastage of time. This is exactly what information we want. It is not necessary that we want all the information from the tool after running it. You may expect cracks or you may not expect cracks at all. If your pipeline is located in the sweet soil, for example Assam, there is hardly any chance external corrosion cracks. Therefore, there is no point in asking for a tool which will measure which will identify the external cracks, internal cracks, longitudinal cracks, circumferential cracks, because all these tools are available in the market, no doubt. But as you go on, making your requirements more and more tough, the cost of the execution is going to increase substantially. Therefore, the tool selection has to be done in a very judicious manner, thinking what do we need. It is exactly that. If we need something, if you don't need something and order for that, you have to pay the price without getting any benefit out of that. Same thing, it is all detailing out what exactly you want. Now, what is the basic difference between MFL tool and ultrasonic tool? As you can see, MFL technique based tool can be conveniently used for liquid and gas transporting pipelines, both. And ultrasonic tool cannot be used for gas pipelines because you need a medium between the sensor and the pipe. Otherwise, the ultrasonic waves will not travel. We know this very well because we apply some liquid whenever we are taking the thickness, residual thickness for a, let's say, any equipment, we apply grease, oil or something and then put the sensor. That scenario is not available here. The second main difference is MFL technique based tool is an indirect method of defect sizing. You see, it is based on the flux leakage. More is the flux leakage, deeper is the defect. That means what we are measuring actually out of this tool, we are not measuring the metal loss, we are measuring the flux leakage basically. And then we convert this flux leakage into the metal loss. Because we'll come shortly, because the tool is calibrated accordingly. The next important terminology in inline inspection is high resolution, because everybody must be knowing that we specify high resolution tool. Now, what is high resolution? Conventional MFL tool has relatively less number of sensors and analog recording. High resolution system is comprised of a greater number of sensors and digital recording. The sensor size and the axial sampling interval which determine the tool resolution and the ability to accurately characterize the defect. That is the basically meaning of resolution. Means higher is the number of sensors, the more accurate result we shall get. There is something else on which resolution depends. Digital recording mandates what is high resolution, containing the same thing, that the continuous signals from the sensors be sampled at discrete intervals. The signal may be sampled as a function of time or a distance traveled. That is, we can sample the signal, let's say every second or every 1/10 of a second or every meter, every 2 meters or every half an inch, 1 inch. But in the realm of inline inspection, time-based sampling is undesirable due to the rather large excursion in tool speeds, because it's not necessary that tool will be moving at a constant speed in the pipeline. The speed of the tool will be changing. Supposing it is falling from a height, obviously tool speed will increase. If it is going up, the tool speed, depending on the profile of the land, its speed will reduce, and so we will not know exactly what is the distance between the sampling. Therefore, instead of taking the sampling on the time-based sampling, we go for distance-based sampling. Conventional MFL tool has relatively less number of sensors and analog recording. High resolution system is comprised of a greater number of sensors and digital recording. The sensor size and axial sampling interval which determines the tool resolution and the ability to accurately characterize the defects. Now, sensor size, I'll just spend a couple of minutes on this. A study was conducted utilizing the test setup depicted in figure 10 to determine the effect of sensor size on the ability to resolve the defect. The defect set was comprised of 3 machined defects. The maximum depth of each defect was 30% of the body wall. The axial separation between the defects was 1.2 inches. The circumferential separation between the defects was also 1.2 inches. Subsequent slide will show what is the importance of this 1.2 inch. It should be noted that according to one of the typical interaction criteria cited in figure 1, these defects will not interact and therefore need to be resolved by the sensor system. These are the 3 defects. Okay, and this is the setup. This is the test setup which was used. The distance between them is 1.2 inches as shown here. And as a result of running one is by 0.25 inch wide sensors. The width of the sensor is only quarter of an inch, that is around 6 millimeters. You get these type of peaks for the 3 defects. If you increase the width of the sensors, in other words, if you reduce the number of sensors, you get more blurred peaks, 0.5 inch, and if you further increase 0.75 inch, you will not be able to distinguish properly these 3 defects. That means the 3 defects cannot be resolved separately. That is, this will not fall under the category of high resolution. At this stage, a very important question should come. Actually, what should be the ideal space between what should be the ideal distance between the samplings? So, ideal distance between the sampling is 0.1 inch, that is 3 millimeters, 3.2 millimeters. That means 2.5 millimeters. Every 2.5 millimeter, the data is recorded into the recorder. And remember, pipeline is several hundred kilometers. We are recording the data every 2.5 millimeters. Okay. So this is what, this is the kind of defect. And here, how the total length shall be measured. Here the defect length shall be considered as from one end to the other end. This figure simply tells us how do we measure the length of the defect, because length of the defect is important. And what should be the width of the defect? The deepest part will be taken as the width of the entire length. When we are doing the analysis, during analysis, this is what is done. You see, now these 3 defects, they will interact, axial interaction may occur. They will actually interact with each other if L3, that is distance between these two, L3 is less than L1 and L2. If L3 is less than L1 and L2, then these 2 defects are going to interact with each other, and then we have to take the total length as a single defect. Similarly, width-wise, if W1 axial, if L3 is less than 1 inch, not less than L1 and L2, if L3 is less than 1 inch, then they are going to interact. And circumferential interaction will occur if W1 is less than 6T, where T is the wall thickness, is this distance between them, then we have to take the complete width as the single defect. This is how axial sampling interval versus peak amplitude. Different sizes of, different sampling rate here. The first one is a continuous sampling. The second one is 0.1 inch sampling rate, then 0.2 inch, 0.3 inch. As you are going to increase the distance, the peak becomes more and more blurred. Here the peak is big, and this signal can be recorded very nicely and analyzed. This is a typical high resolution MFL tool which most of us might have seen. This is a battery unit. These are basically this is the heart, what we call as primary sensor and secondary sensor unit. Primary sensor unit is for external defects. Secondary sensor unit is for internal defects. Then we have odometer. Then we have a computer unit and a recorder, digital recorder here. This is transverse field inspection tool, TFI tool, what we call as. Here the magnets are placed. If you see the typical high resolution tool, the magnets are placed longitudinally, and here the magnets are placed in the TFI tool. In the TFI tool, the magnets are placed perpendicular to the length of the pipeline. Components of a typical MFL tool are drive system, power system, magnetization system, sensor system, data conditioning system. Then factors influencing ILI tool performance. The factors that will be affecting the tool performance are tool design parameters and pipeline design and operating parameters. Magnetization area. That means these are the magnetic lines of force shown in the wall. So low magnetization, medium magnetization and high magnetization. In case of low magnetization, there are no flux leakage. In medium magnetization, we have some leakage, but in high magnetization, flux leakage lines are plenty. Okay. Sensors between the magnet pole pieces measure the flux leakage field. The purpose of sensor system is to convert the flux leakage field into a signal that can be stored and analyzed. Type of sensors, we have two types of sensors generally available. The most commonly used sensor on MFL tools is an induction coil. Induction coil incorporates several turns of fine wire. Sensor is nothing very big. Its idea to tell about this sensor is that it's a very, very simple thing. We know the basic principle, Faraday's law, that a changing magnetic field induces a voltage across the wire. Therefore, no voltage will be induced when there is no defect is present. That means there will be no leakage of the magnetic field. When an imperfection causes flux to leak into the air, a voltage is induced because the flux density is changing. These are the...
Last 5 minutes.
Okay. So induction coil sensors are simple. This is your pipe specimen. The other type of sensors are Hall effect sensors. Only difference between induction coil sensors and Hall effect sensors is that I will go a little fast. Hall effect sensors require power to operate. And if you have about, let's say 360, this is a Hall effect sensor. If we have about 300 sensors installed on a 30-inch tool, that means 1/10 of a watt, that means 30 watt of power is needed. That means the battery which is required, which is mounted on the tool, shall be consumed for this purpose. So generally most of the tool manufacturers, they prefer half the sensors as Hall effect, half sensors as induction coil. This is the magnetization system shown here. In between the two magnets, we have sensors shown here in a circular form. The magnetization system in an MFL tool should produce a magnetic field that is strong, uniform and consistent. Different type of permanent magnets are used. They could be alnico magnets, rare earth magnets and temperature sensitive magnets. Huge amount of data is generated because of number of sensors and the sampling rate. Something like 10 billion data points shall be generated for a 24-inch dia pipeline. If we multiply, if you take the distance traveled for a 120 kilometer pipeline. This is the data generating system. Remember that each sensor is connected to the recorder. So even if there are 300 sensors, there will be 300 cables, and it is available, limits the mileage that can be inspected at any time. Drive system is very simple. The force exerted by gas or liquid pushing on the cup, front cup of the tool, that propels the tool. This is how it is, drive system. Now, operation and execution of intelligent pig inspection, including pre-inspection, inspection and post-inspection activities. The intelligent pigging should be considered as a multidisciplinary activity. This is quite expensive. Therefore, interest of all the departments should be there, and their involvement is very important. One is pre-inspection activity, then field activities, post-intelligent pig run activities. Pre-inspection activities are pull-through tests, information review of the pipeline, pipeline cleaning and geometry assessment, placement of above ground markers. The proposed pull-through test is nothing but basically calibration. This is done at two loaning agencies' works. Test pieces shall have comparable wall thickness as the actual pipe to be inspected. Tool velocity during pull-through should be comparable what it will be in the actual running of the tool. Pull-through test data regarding known defects should coincide within the acceptable tolerance limits with the actual size of defects. This is how we have pull-through. This is feature length. These are the defect lengths which are already known, and within these tolerance limits of plus minus 10%, all the defects should lie. Most of the defects, if one or two defects do not lie, which are shown at 80 or 90, then it is acceptable. Likewise, feature with width comparison, and this is feature depth comparison. This is most important because most of the defects we find that they lie not exactly on the center line, although within plus minus 10%. Information review is nothing that all pipeline features should be known, they should be evaluated. It is basically the first meeting between the intelligent pig inspection agency and the pipeline owner. Then pipeline cleaning and geometry assessment is important. Internal cleaning is a must before launching the intelligent pig tool. Special cleaning pigs such as magnetic cleaning pigs should be deployed. Electronic geometry pigging is most advisable. Otherwise, there is a likelihood that tool may get stuck if there is a dent. Placement of above ground markers. These are magnet markers which are placed every 1 kilometer interval over the ground. Over the pipe by excavating the pipe. When the tool is moving, tool has high magnetic field, and when this magnetic field interferes with the magnet that has been kept over the pipe, it creates a very specific signal. And that specific signal can be seen on the chart, and we know that thus we can very easily locate the defect by putting the magnetic marker system. This is how the magnet is placed. You need not remove the pipe coating. This is an old diagram. Now the more powerful magnets are available where you don't need to remove the coating. Now coils are not used now, so I will not talk about this. Field activities during intelligent pig run, pipeline cleaning, electronic geometry pigging, then pig launching, pig tracking and pig receiving. These are the activities. Of late, XYZ mapping, all the owners require XYZ mapping data during data acquisition. XYZ mapping was developed to determine the three-dimensional graphical pipeline coordinates. Inertial navigation unit is attached with the MFL tool. The major advantage of XYZ mapping is that all the anomalies detected on the pipeline can be located with XYZ coordinates assigned to these features. This facilitates defect identification in the field very accurately without any hassles. This is launcher and receiver. This I will not spend any time.
So your throat is also now dry totally.
Yes, my throat is dry. I will make it lubricated.
The people's eyes have also been, because it's a very long chapter.
It's a very long chapter. No, actually, when I agreed to deliver a talk,
I think that this chapter should be put in 3 parts.
I never imagined that I will get only 10-15 minutes time. I thought I will get at least 45 minutes, frankly speaking.
But you have already got 40 minutes.
Is it? Okay, I'll take only 2 minutes now. I'll finish it quickly. So post-intelligent pig run activities are defect verification. This is most vital. If the defects have been told to us, we should be able to verify that in the field, and then data analysis, and then final reporting. Defect verification is done like this. The tool agency will tell us the location of the defect, feature at 37,489.64 meters. The biggest problem is how to reach at this location. That is what is known as defect location. So these magnets will tell us that from the upstream magnet the distance is so much of the defect, from downstream magnet the distance is so much. So it gets reduced within 1 kilometer, and that much of measurement can be done accurately, so you can reach there. But now even that much effort is not needed. With XYZ mapping we can easily reach the exact spot. This is how the data will be recorded. Each horizontal line represents as a sensor, one sensor, and if there are 100 sensors, there will be 100 horizontal lines. These lines, these vertical lines which are jumbled up together, they show a valve. Like that, there will be selective type of signals for each defect. This is how reporting is done. Tool operational data, pipe tally, list of features, and all those things are there. So this is how what all is given in the tool operational data, and these are the list of features. The most important is ERF, estimated repair factor, will be given, last but one point. Then total number of metal loss, 0 to 9%, 20 to 29%, all that. This means at the interval of 10% each, he will give the defects and depth of defects. That's how analysis is done. These are the fully accepted feature sheets. Then safety precautions during pigging. Accidents appear to fall into three. One is the, normal loading and unloading of pigs and defective equipment such as pressure gauges, etc. Because these tools are quite heavy, so there should be proper arrangement for handling them. Then pyrophoric materials may come out. Pyrophoric means self-igniting material. Hydrate precautions in gas pipelines, particularly for offshore pipelines. Slug collection can take place. This is for multi.
Okay, let's conclude it here.
Let me. I'll just take last slide and I will conclude it here. This is all covered up in one diagram what I have talked so far. Okay. Then there are further, various effects about the tool velocity, level of magnetization, remaining magnetism and all that, which is not very important for the point of view of operator. So I'll close the whole thing here. And
so,
gentlemen, thank you very much.
You are a walking encyclopedia, so by taking technology.
In fact, I
no, I think